Hello students, so today in this video we are going to learn how to derive three equations of motion. So suppose we have a body which is initially moving with velocity v naught, and after time t its velocity becomes v, and during this interval of motion the acceleration of the object which is constant, and that is a, and in this duration the object covers a displacement small s. So very important thing to note here is that equations of motion which are there, three equations of motion, and I will write them. So first equation says that v equals v naught plus acceleration a times t. Second equation gives s is equal to v naught t plus half at square, and third equation says v square is equal to v naught square plus twice acceleration times displacement. These three equations of motion, they are applicable in a very special case, not always. So these are applicable only when the acceleration a of the object is constant. If the acceleration is time dependent or when the acceleration is not constant, these equations of motion cannot be applied. That is very first point to remember always. Okay, so these are three equations of motion, and we can also put acceleration equal to 0 here, and let us see what we get. If you put a equal to 0, then first equation will give you v equals v naught, which is nothing but it says that final velocity will be equal to initial velocity, and this is true also. If acceleration is 0, that means velocity is constant. So if velocity is constant, then final and initial velocities will be equal. And second equation will give you displacement s is equal to velocity v naught or v into t, because v and v naught are equal, and second term will become 0. Third equation also gives the same thing as first equation, v square equal to v naught square. So first and third equation tell you that initial and final velocities are equal, and middle second equation gives you the expression displacement equal to velocity into time, which are very fundamental equations. Okay, so without any delay, let's start and see how to derive these equations of motion, and we will also see there are three different ways through which we can derive these equations. So let's start with the first equation. So first equation is v equals v naught plus a into t. So let's see first way how to derive this. So basic definition of acceleration, if you remember, that says that acceleration a is equal to rate of change of velocity delta v divided by delta t, and if the acceleration is constant, then you can write delta v change in velocity. So initial velocity was v naught and final velocity is, so change in velocity is v minus v naught upon time interval final time t minus initial. Suppose initially the time t equal to 0, then what you have, you can write a is equal to v minus v naught divided by t, and from here you can write v minus v naught is equal to a times t, and you can transfer v naught on the right hand side, then you will have v equals v naught plus at. So this is one way to derive the first equation of motion. You can derive it in another way also, using graph. So suppose you have a graph of velocity time graph. This is time axis, this is your velocity axis, and suppose the graph is like this. Initial velocity is v naught and final velocity becomes v, and initial time is 0, and finally the time is t. So suppose this, we draw a parallel line from v naught to x-axis, means time axis. Suppose this angle is theta, then you know from velocity time graph you can get acceleration by calculating the slope of the graph. So for this velocity time graph, the slope of the graph, that will give you acceleration. So from here you can write acceleration is equal to slope, and what will be slope here? If angle is theta made by the line, by the graph with positive direction of time axis, then slope is given by tan of theta. So in this diagram, this v naught is initial velocity from here to here, and v is final velocity total here to here. So if you want to write this length of side in the triangle, this will be v minus v naught, and the horizontal base of this triangle will be t minus 0, right, from here to here. So in this triangle, if you want to calculate tan theta will be perpendicular divided by base, so it will be v minus v naught divided by t minus 0, and from here you can write, you can transfer this denominator t minus 0, that is t, you can transfer this to left hand side, then it will be at equal to v minus v naught, or from here you can get v is equal to, transfer v naught other side, so it will be v naught plus at. So this is one more way to derive the same equation, first equation of motion, from graph. And there is one more way to derive this equation using the differentiation. So if you have studied little differentiation derivatives, then you know that acceleration is obtained by getting the derivative of velocity. So acceleration definition is dv over dt, rate of change of velocity is defined at acceleration. So you can write a is equal to dv upon dt. So you can write a times dt is equal to dv, right? You transfer this dt on the left hand side, so a into dt is equal to dv. let's write it like this: dv is equal to a into dt, and we are going to integrate this equation. Suppose time changes from 0 to t, and correspondingly at time t equal to 0 the velocity is v naught, and at time t velocity is v. Let's integrate this equation. On the left hand side there is nothing, it is 1, so integration of 1 with respect to v, that will become v from v naught to v, that is lower and upper limit. And acceleration, as I said initially, a is constant, so it can be taken out of the integration sign, so a comes out and it will remain 1 inside, so integration of 1 with respect to time t will be again t, so from 0 to t. And let's put the upper and lower limit, so v minus v naught is equal to a times upper limit t minus lower limit 0, so it is v equals v naught. You transfer this v naught on the right hand side, then it becomes v naught plus a into t. So this is again we got the first equation of motion, but it has been derived from basic derivative of velocity. So I hope you understood these three different ways of deriving the same first equation of motion. Now we will work on second equation of motion. So second equation of motion, that is for displacement. Suppose we want to calculate displacement s. So because it is not a constant velocity motion, velocity is not constant, velocity is changing, but the good thing is velocity is changing uniformly, right? So initial velocity is v naught, final velocity v, so it is changing uniformly, so we can calculate and average velocity. So average velocity here, because it is changing uniformly, so you can write average velocity is equal to initial plus final divided by 2. So you can bring the concept of average velocity here, because velocity is changing uniformly. So you can write displacement equal to velocity times t. So displacement equal to velocity into time. So we are not using a single velocity, we are using the concept of average velocity here. So it is v naught plus v. From first equation of motion you can put v equals this v equal to v naught plus at, and this divided by 2 and whole multiplied by t. So you can multiply this t also inside, then it will be v naught t plus, sorry, you can write this as v naught plus v naught, that will be 2v naught, right? 2v naught into t, plus second term will be a into t will be t square divided by 2. So if you split these two terms on the numerator and divided by 2, so first term will become 2v naught t upon 2, that will become v naught t, plus second term will be half times a t square. So from here you get the second equation of motion, or expression for displacement in terms of initial velocity, time and acceleration. This is one way of deriving the second equation. We can derive this in another way also. Let us see how. Suppose we have graph of displacement and time, no, velocity and time, the same graph we used before. So suppose this is velocity axis, this is time axis, and suppose this is graph is like this as we draw before. So initial velocity is v naught, final velocity is v, and time is from 0 to t for motion. So how do you get the displacement from velocity time graph? If you know the area under velocity time graph, that gives you the displacement. So in this diagram, this shaded area I have drawn, so this shaded area will give you the displacement. So here displacement you will write that is equal to area under velocity time graph. How can we calculate it? So displacement is, let's write it by letter S, and area under graph, this is area is a trapezium shape area. So area of trapezium is given by half sum of parallel sides in the trapezium multiplied by distance between the parallel sides. So in this diagram, if you see, the two parallel sides are, one side is this one, another side is this one. So this is v naught, this is v, so you can put sum of parallel sides as v naught plus v into distance between these parallel sides. The distance between these two parallel sides will be t here minus 0, so it will be t minus 0. So it is half v naught plus v into t minus t naught. So you can write this as half v naught plus v. So again we are going to put v naught plus at in place of this v here. So from first equation we have v equal to v naught plus at, and the second term this is t minus t naught. So t naught is basically 0, initial velocity is 0, so this is 0, t minus here it is 0. So it will again become half v naught plus v naught is 2v naught plus at times t, and let's multiply this t inside, then it will become 2v naught t plus at square and divided by this 2 here. And if you split again the numerator in two parts and divide by 2, then it will become 2v naught t upon 2 is v naught t. The second term will become half at square. So this is again second equation of motion, but this time we have derived this using the concept of graph. And we have another way also to derive the same equation of motion. Let us see how. So we can use the concept of differentiation or derivative as we used before in the case of first equation. So displacement, you can write the definition of velocity. So velocity is defined as rate of change of displacement, v equals ds by dt. So from here you can write ds is equal to v times dt, and we can put the value of v from first equation. So v equal to v naught plus at times dt. So one important thing I think you would have noticed here, that in the second equation we are always using the first equation. So ds is equal to v naught plus at dt. Now we are going to integrate this. Time changes from 0 to t, and displacement, suppose initially the object displacement is 0, so 0 to final displacement s. Now integration of 1 here, nothing is here, so integration of 1 with respect to s will be s from 0 to s, and on the right hand side there are two terms, we will integrate them separately. So first term, if you open the bracket, it is integration v naught dt. V naught is a constant initial velocity that can be taken out, and inside there will be 1 only, so integration of 1 with respect to time will be t from 0 to t, plus second term will be integration of at dt. A is again constant, can be taken out of the integration sign, and integration of t with respect to time will be t square by 2. So it is from 0 to t. Now let's put the values, upper and lower limits. So on the left hand side it is s minus 0, on the right hand side v naught, and it is t minus 0, plus second term will be a times t square by 2 minus 0. So if you simplify this, you can simply write it as is equal to v naught into t, plus this second term will be half a t square. So again we got the same second equation of motion, but this time we have derived it using the concept of differentiation. Now finally we are coming at third equation. So third equation is equation which have no term of time into it. It has only initial velocity, final velocity, acceleration and displacement. And in all the three equations you can notice that there are four variables involved. One is initial velocity v naught, one is time of duration of motion, and there is acceleration and displacement, and final velocity, right? V naught, v, time, acceleration, displacement. 1, 2, 3, 4 and 5. There are 5 variables involved, and you will see that in each of these three equations there are 4 variables involved and one is not present. Like in the first equation, v naught, a and t are present, but s is not here. In the second equation, s, v naught, t and a are present, but final velocity v is not present. In the third equation, similarly, time is not present, other 4 variables are present. Okay, so in the third equation, time is not involved. There are only initial velocity, final velocity, acceleration and displacements are involved. Okay, let's write third equation. So we can't derive the third equation using the graph because we usually have the graphs of velocity time or displacement time, but we don't have, we usually don't discuss graph about velocity and acceleration or velocity and displacement. So third equation we are not going to derive using the concept of graph, but we will use two different methods, one using derivative, another a simple method. So first equation of motion, we have v equals v naught plus at. So we can proceed directly by squaring both hand sides of this equation. So you will write v square equal to, on the right hand side, square of v naught plus at whole square can be written as using the formula of a plus b whole square. This will be v naught square plus a square t square plus 2 times v naught a t, right? So this is v naught square. In the second, in these two terms you can take 2a common, and what can you write in the here? In place of a square t square you have taken a common, but no 2 is there, so you need to put half here, and 1a has been taken common, t square will remain, plus on the second term you have taken 2a common, so remaining is v naught times t. And if you look carefully, this term inside the bracket from the second equation, if you compare, this is displacement. S is equal to v naught t plus half a t square, or half a t square plus v naught t. So this is displacement s. So finally we have v square equals v naught square plus 2as. This is your third equation, which we have derived just by using the first equation and squaring both hand sides of this equation. We can derive this third equation using the concept of derivative also. Let us see how we can do that. So you can write acceleration as we did in first equation of motion derivation, that is written as the rate of change of velocity, a is equal to dv by dt. In this equation you can introduce the ds variable in numerator and denominator like this. So you can write ds upon dt into dv divided by ds. So ds has come into numerator and denominator, so it will get cancelled. It overall it doesn't make any change. Overall we have dv upon dt only as we had before. Okay, so ds upon dt, this is rate of change of velocity that can be written as velocity v, sorry, rate of change of displacement it is, which can be written as velocity, and second term as it is dv upon ds, and on the left hand side you have a. Now we are transferring this ds on the left hand side, so we can write a into ds is equal to v into dv, or you can reverse this equation, so you can write v dv is equal to a ds. Now we are going to integrate this equation. So integration, on the right hand side the variable is displacement, so displacement varies from 0 to s, which is the final displacement. Initially it is 0, and on the left hand side the variable velocity, and velocity changes from v0 to v. Now we will integrate this both hand sides of this equation. So integration of v with respect to v, that will be v square by 2, and lower limit is v0, upper limit is v, equal to a can be taken out of the integration sign because it is a constant, and integration of 1 with respect to s will be s, so 0 to s. Now let's put the upper and lower limits. So it is v square by 2 minus v0 square by 2 is equal to a times s minus 0, and you can write v square minus v0 square together in numerator, so it is v square minus v0 square divided by 2 is equal to a times s. So you can transfer 2 on the right hand side, so it is v square minus v0 square is equal to twice of as, or finally you get the third equation of motion as v square is equal to v0 square plus 2 times as. Okay, so you saw that we derived these three equations of motion in three different ways for equation 1 and 2, and two different ways for equation 3rd. Okay, so this equation of motion, as I said before, you need to remember that these equations of motion can be applied only when acceleration a is constant. If acceleration a is time dependent or it is not constant, then these equations of motion will not be applicable. You can get some other form of equation of motion, but for every different situation you will get a different equation of motion. But yeah, for constant acceleration these three equations are well popular and questions you get based on them. And one very familiar situation is motion under gravity. So you know, motion under gravity, the acceleration is acceleration due to gravity, and acceleration due to gravity is constant because its magnitude is 9.81 meter per second square. That is if you are not changing the place. Usually it is taken 9.81 meter per second square is the magnitude. Direction is also always directed towards the center of earth or always vertically downward. So this is a kind of acceleration which has constant magnitude as well as constant direction. So for motion under gravity, that is a kind of constant acceleration. So in constant acceleration situation you can apply equation of motion. So for motion under gravity situations you can apply these equations of motion. And one more last thing I would like to tell you before going. So these equations of motion we have derived for simple straight line motion, but these equations can be applied for motion in 2 dimensions or motion in 3 dimensions. So in short, I can tell that in along every direction, like every axis or x-axis, y-axis or g-axis, you need to apply these equations separately. So maybe more about this I can discuss in my another video. But yeah, but these equations of motion you need to apply independently along all the 3 axes or along all the 3 different directions. And the common factor shared by all the 3 directions will be time. So time will be common in all of them, but velocity, acceleration, displacement, those you need to take in a particular direction which you are considering for under study. Okay, so I hope you understood this and you enjoyed today's video where we saw how to derive the equations of motion using 3 different ways.